Our first speaker this afternoon is Mario Bergeron. He is a technical marketing engineer at Avnet Electronics, and he's going to be talking about system-level design for embedded vision with FPGA-based programmable SoCs. Mario.
Perfect. All right. Thanks, everyone. Good afternoon. My name is Mario Bergeron. I work for Avnet. Does anyone know what Avnet is? Well, it's a distributor. So we don't necessarily create IP or products. We sell parts for the companies that create products. So what we do at Avnet is we operate in over 80 countries, connecting 100,000 customers to the technology that's created by the manufacturers, a lot of which are represented here at the Embedded Vision Summit. And the group that I work for specifically, what we try to do is combine technology from different manufacturers as system solutions. And we do this in form of reference designs, development kits, trainings, online, or live. So that's kind of what I do in the... So I work a lot with these new class of devices that I've called FPGA-based programmable SoCs. You won't find that specific verbiage anywhere on the internet or on products. I've purposely taken a step back and made it like a more generic verbiage to not be specific to one manufacturer. So I'm just going to describe what these devices are, what the typical development cycle looks like for these devices. I want to share some of the challenges that you may run into if you use these devices. And just to conclude, I also want to mention that a lot of these challenges are being resolved with new emerging software tools. So if we get started, what are FPGA-based programmable SoCs? Well, they're basically devices that bring in the best of both worlds, right? They have industry standard processors that take the software side of things. So you can use this to leverage operating systems and legacy code, existing libraries such as OpenCV. You also have the hardware aspect, which is brought in with FPGA technology, right? So for those who are used to doing hardware design with FPGA technology, you can actually get higher performance for specific processing algorithms. You can put standard or custom interfaces into your product, which allows you to give you some differentiation. And you can also create, specific to your application, some accelerators that will make your solution unique. So whether it be, right, the Smart Fusion 2 from Microsemi, the Zinc all-programmable SoC from Xilinx, or the FPGA SoC from Altera, all of these devices are basically combining industry standard ARM processors with FPGA technology into one single device. And they have a lot of interconnect capacity between these two technology in that one single chip. So these devices have several advantages that I want to talk about. Differentiation, being able to put the interfaces that are specific to your application and the accelerators that are specific to your application, that gives you differentiation with respect to your competition. They also give an advantage for integration. So when compared to an equivalent two-chip solution where you may have some kind of processor in addition to an FPGA, having this into a single device can give you saving in terms of board space, cost, and power. Their flexibility and scalability. These devices come in low, mid, and high-end devices. So there's a very large a range of devices that you can choose from. So you can choose the one that really fits your application in terms of the processing capabilities of each device. And of course, performance. Performance not only in terms of compute operations per second, but also in terms of getting low latency in certain applications. So they give you a lot of good performance. They do have some disadvantages, especially if you're coming from a software background working with a standard processor. They will give you a new item that you need to work with, which is the hardware design, right? So if you're coming from a software background, these devices will give you may pose a challenge for you where you now need to get your hands, roll up your sleeves, and do some hardware design. And they are fairly complex to get up and running with, get started with. So what does a typical development cycle look like for these devices? Well, if you compare them with an application-specific processor, the processors, when you receive the devices, are ready to go. You can start programming with them. But when you buy the chips, the hardware component is empty, right? It's a clean slate. It's actually a big advantage but it has the challenge that you have to design this component of that device for your application. So that's the reason why the first step is usually creating a hardware platform in devices. You need to put in some standard interfaces. I put 2 here on the image. It could be HDMI for an output or MIPI for camera input. You can also put some custom interfaces, something that would not be able to connect to a DSP or a processor, or something that's specific to a solution that you're providing. Once you've got the hardware infrastructure in place, your interfaces if you want, then you can start saying that you can start to compare with an application-specific processor where you have your interfaces in place. Now, this is where our customers will usually start developing their software application. So probably leveraging operating systems on these devices, leveraging legacy code or existing libraries, such as perhaps OpenCV. The one step that all of our customers usually do, because of the 2 technologies, you want to make sure that the system that you're creating, because you're creating a unique architecture, you want to make sure that it's giving the performance that you want. So there's usually a system profiling phase that needs to be done here. And on the software side, in the processors, this uses standard processor tools, either open source, GNU, or using the ARM JTAG emulators. And on the hardware side, this will be specific to the manufacturer, right? So Microsemi, Altera, Xilinx still have their own technology, which allows you to put a logic analyzer in the hardware, giving you visibility to all your nets if you want. So it's very powerful. And usually what you want to do is maybe when you're developing your product, select a slightly larger part so that you could have room in that hardware component for the logic analyzer, which will help you debug, measure the performance of that hardware component compared to the software. And then finally, once you've got your application running on the software side, which is usually where things start out, you may want to profile that application and determine what may go to hardware for acceleration. And as the final phase, this is usually where you would stick in your hardware accelerators specific to your application on these devices. So this is just quickly the typical development cycle that you would see with these devices. So one thing to point out, if you want to compare it, if you're coming from a software background, that first step, just laying out that hardware infrastructure is a new portion to the development cycle. And at the very end, if you're putting your own hardware accelerators, that's another one that changes as well. So I want to talk about a few challenges. The first one I want to talk about is balancing the load. What do I mean by that? It's basically that the 2 technologies in these devices have quite different capabilities, right? If we look at the processors, the ARM processors, for the Altera and Xilinx ones, they have processors running at 1 gigahertz. So this can give you 1 giga operations per second per core, right? And from what I've seen people implementing on these processors, you can achieve real-time vision algorithms at about VGA resolution. That's like a ballpark number that you would achieve on the software side using only the ARM processors. Whereas on the hardware side, in this FPGA technology, the capabilities are much more impressive. You can get anywhere from hundreds of giga operations per second to several tera operations per second of compute power. So in the hardware, they're very capable of achieving 4K resolutions that we hear a lot about, or even thousands of frames per second if you're going for very high-rate machine vision type applications. So the challenge when you take your application and target it to these devices is balancing the load on leveraging the software and the hardware side, but in a way that makes best use of both technologies. So one way that you could deploy your algorithm onto these devices would be to keep all of the processing that operates on images in the hardware. These are the ones that work on the highest data rates, right? If we look at high definition video, algorithms may be simple, hundreds of operations per pixel, but we're working on a lot of pixels, right? It could be hundreds of millions of pixels. So this, as a ballpark, it could represent hundreds of giga operations per second of processing requirements. So putting this on the hardware definitely makes sense. And even the feature extraction, they still work on images as the input, but they create something else at the output, right? Metadata. So this is where your data rates can start to come down. And this is where it would make sense to pass the puck to the software component, which may have much more complex algorithms. It could be tens of thousands of operations per feature. But instead of working on millions of pixels, it could be just thousands of features per second. So that's in the range of mega operations per second. So this could be one way of balancing the load on these devices. I want to talk about one example that we're actually showing at our exhibit table. It's an example that was created by Xylon. They approached this in a slightly different manner. As you can see, if we start, so they implemented a face analytics algorithm onto one of these FPGA-based programmable SoCs, and it's an algorithm that provides real-time 3D head pose. So they're detecting a face and tracking it, and then they determine within that region of interest facial expressions, whether your eyes are open or closed, and where you're looking at. So you can think of automotive applications perhaps, or some kind of control. And this is what their implementation looks like. So they start off by doing a lot of the high data rate image processing right in the hardware. Just as a legend, my green blocks are what are implemented in hardware, and the blue block is what's implemented in software. So they also do some color space conversion where they move to monochrome because this algorithm does not need to work on color. And then they pass the image to the software. And the software, the ARM processors, are actually doing most of the analytics algorithms. Now, the way that they reduce the data rates to balance the load between the hardware and software is they actually resize the image. So color space conversion reduces the data rates, and they also reduce the image size by actually a factor of over 50. And this is how they achieve the data rate reduction to balance the load between the hardware and the software. And in addition, they also, once they had detected a face, to track that face, they're using a cross-correlation algorithm. So they actually move this to hardware to accelerate the algorithm one step further. So that second green box. And finally, they generate some graphics, which gets mixed up with the original video just for visual representation on the monitor. So the second challenge I want to talk about is building the infrastructure. This kind of has the scope where if you're used to working with a processor and where all the hardware is set up, the device drivers are available. If you start working with these devices, this could be a challenge for you, right? You need to create that hardware infrastructure, and you may also need to create the device drivers that go along with it. So most of our customers are fairly comfortable working with processors, and they're also very comfortable working with FPGA technology. The challenge emerges when these two worlds collide, right? So it's the interaction between the two. So these devices have a lot of interconnect. Specifically the Altera and the Xilinx devices, they have over 100 gigabits of interconnect bandwidth between these two technologies, between the processors and the FPGA, the hardware side, right? And the way that you can interact, move data between the two uses a lot of, you can use memory, shared memory. There is on-chip memory that it's available. There is L2 cache, which is basically a bridge going to the external DDR. But these are three types of memories that you can use to interchange data. There's also a lot of DMAs and interrupts in the system allowing to do the synchronization. And there's a lot of interconnect and quite a few choices of interconnect. And this is where you can choose to create your own architecture, right? So there's general purpose ports, which are basically lower bandwidth that you wouldn't use to transport large amounts of data. You would use these to do configuration of your hardware system, configure IP cores. There's high-performance ports, which are very good at transporting large amounts of data, like video streams, high-speed ADCs, DACs. And their downside is they do have a startup latency, right? They'll get latency to get that data stream flowing. And there's another type of interconnect that's available that comes from the ARM IP portfolio, and that's the accelerator coherency port. And basically what this port does is it can also give high bandwidth, but on a limited amount of data. It's basically, it'll get you the performance if that data can fit in the L2 cache. I should be drawing these interconnects as I talk about them. The high performance port basically will be used to transport data to the external DDR memory. And the accelerator coherency port, which gives you high bandwidth with smaller data sets, but its advantage will be lower latency, so you get faster response times. Right? We could think of just orders of magnitude for the high-performance port. It could be hundreds of cycles of latency, whereas the accelerator coherency port could be just tens of cycles, so much faster response times. So as you can see on the hardware side, that green box, you define which interconnect you will use in your design, and you can iterate and change and compare them. The challenge is that every time you make a change with those interconnects, you need to create a new hardware design. And that's actually can get pretty involved when you're, right? It's much longer to create hardware than it is to write software, from my experience. So here's that same example from Xylon, just drawn out differently. I've represented the L2 cache and the DDR as layers between the software and the hardware, just to show that the L2 cache is closer to the software, right? It gets a lower latency. So this is how they've implemented their data flow between the software and the hardware. So on the output side, the graphics are just basically sent to the external DDR, and that's just pulled out to the monitor. For the cross-correlation accelerator, they're using the accelerator coherency port. And in their initial implementations, because this is actually video content that's being passed around, they started by using the high-performance ports in their implementation. And what they found is that on that input side, as that resized image came in, there was actually some latency involved in just in the overall chain of processing. But the biggest unexpected surprise for them was that their accelerator, the cross-correlation, actually did not achieve any acceleration because of the latency involved with the high-performance ports. So they actually moved this to the accelerator coherency port. And in their case, because they're working with a resized image, they're working with chunks of data that fit inside that L2 cache. So they were able to get 4 to 5x acceleration on that cross-correlation piece. So the point I wanted to make with this diagram was that inevitably you may need to experiment with different interconnects and change them. And that brings the challenge of doing all these iterations of hardware designs, if you want. So in addition to the hardware, software developers, especially if you're using an operating system, will need device drivers to access this hardware. So in these devices, since you're creating custom hardware, you will also need to think about creating device drivers for this hardware. So we ran a survey with our field team, our FAEs, asking about what our customers' experience was with OS-related development. So this includes device driver development. And this is the response that we got. So basically, 15% of our customers planned and executed the OS portion, the Linux driver development, without any hitch. So they planned it correctly and they executed it correctly. 38% of our customers underestimated this effort, but still were able to execute on it. Now, if we take the green and the purple pies together, that's 40%. 40% of our customers were actually overwhelmed with the device driver, OS-related development part of creating a product on these devices. So 20% of them just took a hit for the development time, and half of them actually went out to external contractors who are specialized in doing this type of development. So I guess the point I want to make is don't forget to factor in if you're using these devices, you'll be creating custom hardware. Don't forget to create those device drivers in your development cycle. Right? The third challenge I want to talk about, choosing the right IP. I'll use a use case for this. We have Python is an image sensor from ON Semiconductor, which are represented here. It's a very scalable image sensor family. If we look here, I have 4 of them. The first one, the Python 300, actually has 4 parallel data channels coming out. The 2 middle ones, Python 2000, 5000, has 8 channels, and the largest one, the 25K, has 32 channels of data coming out. So this image sensor, it's a proprietary interface. It's a custom interface that you will not be able to connect up to a processor or a DSP. You do need hardware, either ASIC or FPGA. So this is an image sensor family that you can connect up to these devices. So as the data comes in, as these parallel data lanes, it's actually at a very reasonable frame rate, right? The pixels come in at 72 megahertz per second, which is very achievable for FPGA technology. But if you merge all these pixels into one single stream, this is where the bandwidth and the pixel rate gets very high. For those 4 channels, we're talking about 288 megahertz pixel rate. And for the larger one, we're talking about 2 gigahertz of pixels per second. So the challenge that comes with this is if you're using IP cores And if you take the IP cores from the manufacturers, their IP cores are pretty generic implementations. They operate on 1 pixel per cycle. And if you were to do this with the smallest Python image sensor that I talked about, which had 4 lanes at 72 megahertz, you would need to combine these pixels into one single stream of pixels before being able to feed it to these IP cores. So that you would bump up your pixel rate to 288 megahertz. The thing you need to know with these devices is that if you look at the lower cost ones, you'll typically run out of steam at 150 megahertz. If there's very good hardware designers in the room, they may be able to achieve more. But rule of thumb with the smaller end of these devices would be 150 megahertz. It's very easy to implement a hardware design with this. So this corresponds to 1080p 60 resolution, very decent. But for something that needs more bandwidth, like these Python image sensors, you've run out of steam, right? Okay, well, 288, what if I go to one of the larger devices? Well, this one has a limit of 300 megahertz, right? So you could use that. But our customers would not use that higher end device because it's not cost effective. It would make more sense to use the lower cost. And this whole discussion is actually pretty ridiculous because it's not a limitation of the device. It's a limitation of the IP core that's only operating on 1 pixel at a time, right? So the challenge to make full use of the hardware in these devices is to use IP cores that can operate on multiple parallel data channels, right? Just as an example, if we talk about 4K, 2K video resolution at 60 frames per second, that's 600 megahertz of pixel rate, right? So if we want, it would be possible to implement some kind of processing on a 4K 60 resolution on the lower cost devices using 4 data channels, or on the higher end devices, which has a limit of 300 megahertz, using 2 parallel data channels. But the point I want to make is, make sure you determine your pixel rate to determine if you need to go and use parallel data channels. Because there are IP providers that have IP which operate on parallel data channels. Xylon, the one who created the face analytics demo that I talked about, their cores support 1, 2, or 4 pixels per clock. And another company who created a talk today, Avnet Systems, and they also have a table. They have IPs that support 1, 8, or 16 pixels per clock cycle. So they're involved in data center applications where a lot of video image processing is involved, and they do a lot of parallelization to get a lot of acceleration. So how much time do I have left, Phil? I'm good, okay, all right. So I talked about 3 challenges, right? Balancing the load, building up your infrastructure, and in some cases, the need for parallel data channels for these IP cores to get efficient implementations. I don't want these challenges to discourage you from using these devices. We have customers that are very successful in using these devices. You just need to know about and plan for these challenges. And one thing that's very interesting is that most of these challenges are actually being resolved with new emerging software tools, right? We have MathWorks who create some development tools which will address all of these challenges. The one that I want to talk about, that I've chosen to talk about, is from Xilinx. So Xilinx software-defined tools. Basically what they've done is they've created a tool where the design entry is being done from a software environment, right? So everything's specified in C or C++. They have a system optimizing compiler which allows you, using pragmas, to target some code to software, in which case it's using the standard compilers and linkers that you already have in place for software. And when you want to target something for hardware, it makes use of another tool, which I have in the second bullet there, HLS, high-level synthesis. And what's really interesting about this tool is, in addition to creating the hardware, which would be the accelerator, they're also creating device drivers along with that accelerator. In addition, they're also creating the interconnect, right, using either the GP, the high performance, or the accelerator coherency port. They're creating that infrastructure, connecting up the software and the hardware. And this is a big plus, in my opinion, because it allows you to, by just using this tool and changing the pragmas, select which interconnect you want to use, and it allows you to explore different architectures in the device. So it increases your productivity significantly. And the tool, usually, it comes with platforms which are created for specific development kits. And basically what these platforms provide is pre-built infrastructure, right? So you've got the infrastructure, and you've got your drivers in place. Then you can start working from a software environment to target an application on the software and on the hardware. So in essence, the way I see this is they're almost providing you an environment similar to an application-specific processor where you've got your hardware in place and you can generate your custom hardware. So very interesting tool. So in conclusion, if you use these devices, make sure you plan the time to build the infrastructure that you need, right, on that hardware portion. So this includes the hardware, the interfaces, your accelerators, and the interconnect. Make sure you think about on the software, your device drivers to enable your software developers to access that custom hardware. If you're selecting IP cores, make sure you calculate your pixel rate to determine if you can do this in 1 pixel at a time per cycle, or if you need IP cores that allow you to do parallel data channels. And while you're at it, make sure that these IP providers provide device drivers for these cores. And I would seriously recommend to consider using these emerging tools like the Xilinx SDSoC that's coming out, which can accelerate your productivity, right? These tools, by generating these hardware components and the interconnect as well, they will increase your ability to explore different architectures. So as you're profiling your system, tweaking it, you can do these iterations in a more productive fashion. And that's the end of my talk. So I'd invite you, if you didn't already, to come to the Avnet table. I'm basically showing one of our kits, showing the Python image sensor that I talked about, and we're showing that demonstration that I mentioned that was created by Xylon, which is the face analytics. So it'll detect your face, track it, determine if your eyes are open or closed, and which direction you're looking at. And we also have a module, which is an image sensor from Toshiba. And my last slide is just references if you want more information, some links where you can get more information on these devices. Thank you.
Wonderful. Thank you very much.
So I guess I'm taking questions now.
We have time for 1 or 2 questions. So please raise your hand and we'll have a microphone runner come to you. I found the, right here, great.
When does the SDSoC toolset, do you know when Xilinx is planning to release that?
It's coming out publicly in June, I believe, yeah.
Okay, well, thank you so much.
All right, thank you.